Next, we discuss endfire and butt coupling. This is possibly the most popular technique to couple light into and out from the waveguides. We simply shine light to the edge of the waveguide by a lens, and this is the endfire coupling configuration. Alternatively, we bring a waveguide, such as an optical fiber, to the close vicinity of the waveguide. This is the butt coupling configuration. Now we are interested in how much of the incident light couples to the modes of the waveguide and what other conditions we might need to consider. The waveguide modes are orthogonal, and this means that the following integral holds. Intuitively, we can understand this condition by examining the field profiles. If we multiply the first and second order mode and integrate the multiplied modes, we obviously get 0. And this applies between any two modes of the waveguide. In such a case, the waveguide modes form an orthogonal basis, in a bit similar manner that sines and cosines are used in Fourier analysis. We can now present the incident field as a weighted sum of these orthogonal modes. And now our first task is to find the amplitudes AM of each mode to obtain a presentation of the incident field. First, we can multiply both sides with a complex conjugate of another mode, En. Next, we integrate both sides and use orthogonality. We can see that by replacing m's with n's, the sum can be removed and the amplitudes of each mode can now be written using the mode fields as so the amplitude constant can be evaluated from the incident field and the mode field in question. Coupling of power to an individual mode can be defined as a ratio of power of the mode divided by incident power. By inserting the expression of the constants, and by simplifying this expression, we obtain the so-called overlap integral, which describes coupling between incident field and individual modes of the waveguide. Let's take an example. Here we couple a Gaussian field into a multimode waveguide. The width of the slab waveguide is 3 micrometers and the input field is a Gaussian having the width of 400 nanometers. And we neglect possible reflections at the interface between the incident field and the waveguide. Here, 6 first modes of the waveguides are shown: fundamental, first order, and up to 6th order mode. Now we calculate coefficients AM between the modes and the incident field. And further, we can evaluate the coupling efficiency for each mode. Here we can see that about 55% of the power is coupled to the fundamental mode. Note that coefficients for odd modes is 0 due to symmetry of the fields, and more than 97% of the power is already coupled in these three modes. We can now also check how well the incident field is constructed using the modes m equals to 0, 2, and 4. The match is pretty good, yet not perfect, and we should use more modes to get a better match.